Hold any object up in the air above the ground and let go, and it will fall. Galileo measured this acceleration as negative 9.8 meters per second squared on Earth. This acceleration is true for any object, no matter its size. All objects fall at an acceleration of 9.8 meters per second squared on the planet Earth. However, holding one or two in my hand, these things weigh differently. And what Newton said was that the relationship of that experience is a measurement of the force and not the measurement of the fall based on the acceleration. That force is called weight. Weight is a force due to gravity, but is not gravity, quote unquote, as described by Galileo. Galileo was describing an acceleration that is later relabeled as lowercase g. This lowercase g is the acceleration of a falling object, but is not the force experienced by an object as it falls. That force is the effect of that acceleration on the particular object's mass. So in other words, if I think about it as F equal to ma, where I'm not looking at the net force, but just the force based on a particular acceleration, in this case, F due to gravity is the object's mass times the acceleration that we are aware of, at this case, mg. This is a scalar calculation of the amount of force due to the acceleration of gravity on Earth. This force is always towards Earth, which is why it's labeled as going down in most cases, and in many cases will contain a negative sign due to the acceleration of gravity. And so as a vector, we would say that this is in the same direction as that. But it is very important to note that this is a force, g is an acceleration, and it can be proven quite simply by comparing objects 1 and 2. If I look at object 1 falling in space, the total forces acting on that object while it's in the air as a free body diagram would be pointed downward. This force would be F of g in this particular case. If that is true, then the sum of the total forces, or the net force, is F of g only. This is true because F of g is the only force as long as the object is still in the air. If the summation of the total forces is m times a, and we now know that the weight is m times g, no matter what the mass is, a is g. And so if I resolve this for a secondary object where the mass is much bigger, the weight force is much bigger, but again, the total forces acting on that object while it's in the air are F of g. So the sum of the forces is F of g. The sum of the forces is equal to m times a. And now we know that m times lowercase g is how we calculate weight. So once again, the mass cancels, a is g. And so it holds to Galileo's experience that the objects fall at the same acceleration, but it also holds true to Newton's description that the acceleration is inversely proportional to the mass and directly proportional to the force. So for object 2, it experiences a larger force, but it has a larger mass. And so since force is directly proportional and mass is inversely proportional, those two effects cancel out. And so A is always 9.8 meters per second squared towards the Earth. What will be significantly relevant is when an object is actually finally at rest on the ground. If object 2 has fallen, hit the ground, and is now sitting stationary, it's important to note that if it is sitting stationary, there must be a force acting up to cancel out the weight force acting down, because otherwise it would be falling as it was in the previous picture. And so in terms of the forces, we discover that there is a force from the ground pushing up. This force is perpendicular to the ground and is called the normal force, F of n. The normal force is a perpendicular contact force that's applied when an object makes contact with a surface. In this case, it would be the ground. In many cases, it's a roadway or a ramp, but it is always directed perpendicular to the surface. And we'll study that more when we talk dynamics in the coming weeks.